Imagine a world where AI doesn't just predict the next word, but understands the structure of reality itself. Not by memorizing data, but by learning the fundamental laws that govern how things change over time. That's the promise of a new frontier in artificial intelligence, physics-informed neural networks, or PINNs. These aren't just another tweak to deep learning. They represent a paradigm shift in how we teach machines to reason about the physical world. At their core, PINNs are neural networks that don't just learn from data. They also embed the laws of physics directly into their training process. Traditional deep learning models are data-hungry. They need massive datasets to recognize patterns, but they often fail when faced with situations outside their training distribution. They might predict that a bridge will hold under a load they've seen before, but crash when asked to handle a novel stress condition. Why? Because they don't know the underlying physics. They've just learned correlations, not causation. PINNs change that. Instead of relying solely on data, they integrate differential equations, like Newton's laws, Maxwell's equations, or the Navier-Stokes equations, into the loss function of the neural network. This means the model is trained not just to fit observed data, but to satisfy the known physical laws. The result? A model that generalizes far beyond its training set, because it understands the rules of the universe, not just the examples. Let's break down how this actually works. Suppose you're trying to model heat flow through a metal rod. The governing equation is the heat equation, a partial differential equation, PDE, that describes how temperature evolves over time and space. Delta U/delta T equals alpha 2U. Here U is temperature, T is time, X is position, and alpha is thermal diffusivity. A traditional model might collect temperature readings at various points and times, then train a neural network to interpolate between them. But it would have no idea what happens if the boundary conditions change, or if you suddenly apply a heat source in a new location. Now with a PINN, you define a neural network U theta, X, T, a function parameterized by weights theta that approximates the temperature field. During training, you compute the residual of the PDE, the difference between the left-hand side and right-hand side of the heat equation, evaluated at a set of collocation points across the domain. You also add terms for initial and boundary conditions. The total loss function becomes L equals L data plus lambda 1 L PDE plus lambda 2, L initial plus lambda 3 L boundary. Where L data measures how well the network matches observed measurements, LPDE penalizes violations of the heat equation, and the other terms enforce initial and boundary constraints. The hyperparameters lambda 1, lambda 2, lambda 3 balance the contributions of each term. Now here's the magic. The network isn't just fitting data, it's being forced to obey the physics. Even if you only have sparse or noisy measurements, the PINN can still produce a solution that's physically consistent. It's like teaching a student not just to memorize answers, but to understand the principles behind them. But PINNs aren't just good for simple PDEs. They're being used to simulate complex systems like fluid dynamics, structural mechanics, and even quantum systems. In aerospace engineering, researchers use PINNs to predict airflow around aircraft wings with fewer computational resources than traditional CFD solvers. In materials science, they model crack propagation in metals by embedding fracture mechanics into the loss function. In climate modeling, PINNs are helping simulate ocean currents with high fidelity, even when observational data is limited. And the best part? They can work with minimal data. In many real-world scenarios, collecting full-field measurements is expensive or impossible. But with PINNs, you can use just a few sensor readings, say temperature at 3 points on a beam, and the model will infer the full temperature distribution, guided by the underlying physics. But it's not all smooth sailing. There are challenges. Training PINNs can be numerically unstable. The gradients of the PDE residual can be very sensitive, leading to vanishing or exploding gradients. The choice of collocation points, where the PDE is enforced, can dramatically affect performance. And balancing the loss terms is tricky. If the data loss dominates, the model may ignore the physics. If the physics loss dominates, it may overfit to the equations and ignore real-world measurements. To address this, researchers have developed advanced training strategies. Adaptive sampling dynamically places more collocation points in regions where the PDE residual is highest, where the model is struggling. Multi-scale architectures help capture both global behavior and fine-scale features. Some even use physics-aware regularization or hybrid models that combine PINNs with traditional solvers. And the future? PINNs are evolving into neural operators, which learn mappings between entire functions, not just point-wise solutions. These models can solve families of PDEs with different boundary conditions, initial states, or geometries, all with a single trained network. Imagine training one model to solve the Navier-Stokes equations for any shape of pipe, any fluid, any flow rate, just by changing inputs. That's not sci-fi. It's happening now. But perhaps the most profound implication is philosophical. PINNs suggest a new way of thinking about intelligence. Rather than building models that memorize data, we're building systems that understand the world by encoding its laws. This isn't just about better predictions. It's about creating machines that can reason, extrapolate, and innovate, not just imitate. So the next time you hear about AI solving complex problems, remember, the most powerful models aren't just big, they're smart. They don't just learn from data. They learn from the laws of nature itself. And that's where the real revolution begins.